Good afternoon, everyone. We are from Testia, a subsidiary of Airbus, and you may have come across our company in the past as a provider of NDT products and NDT services. But we are here today to show you that the portfolio of Testia is actually much bigger than that. So our presentation today will be on monitoring technologies to monitor actually the manufacturing processes of composite parts and not only the manufactured parts in the end. I'm sharing the presentation today with my colleague Benjamin, who is based in Rennes in France, and my team, we are based in Ottobrunn, close to Munich in Germany. We structured our presentation to show you the different solutions that we have along the whole process chain. So we will start with PF Inspect, which Benjamin will be presenting to monitor the layup of fibers. And then I will take over showing you our inline vacuum monitoring system and our inline infusion monitoring system. And we will cap it up with some technologies that we have also to monitor the cured parts. So as I said, we are covering the whole manufacturing chain for composite parts, starting with the inspection of raw materials, then continuing with solutions, how we can monitor the layup of the fibers, and then also the vacuum bagging, and if you have an infusion process or an RTM process, the infusion. Then coming to the cure, the trimming also, and the quality control of the finished part afterwards.
Thank you. And for myself, I will run you through PF Inspect, which is our solution dedicated to inspection. As Christopher says, we can apply this inspection in several steps in the manufacturing process. The first one would be the inspection of raw material. So to do so, our solution is a scalable solution that can be applied over a wide range of speeds and width of inspection. You can, with this solution, measure orientation with a pretty high accuracy of 0.1 degrees, and you can inspect your production with rates up to 2 meters per second. The defects that you are able to monitor or to detect are quite common. The first one is measurement of fiber orientation. With our solution, we are able to, as I said earlier, measure orientation with a precision about 0.1 degree. Then we can also detect missing knittings or missing stitches. We have also ability to detect and measure gaps in the fabrics. Fuzzballs or foreign objects, either on the top surface or inside the materials. And as I already said, FODs. You can also apply the same processes to monitor your preform system. The idea here is to inspect ply per ply the surface of your production. The system can be embedded on the robot gripper to monitor the position and the absence of defects in all the plies. Once again, the maximum speed that you can reach with such a solution is up to 2 meters per second, and we have an high accuracy of localization of the ply edges towards tenths of a millimeter. The defects that the system can inspect are the same that on raw material, even if it's in preformed shape and more complex 3D geometry. And you add another possibility to detect and position the ply edges to find if the ply is the right one that was deposited and if it's located at the right position. Once the part is laid up, you will then move to bagging. And to monitor those steps, Christopher will present you the solution that his team has developed.
Thank you. So I will present our inline vacuum monitoring system, which is a system that can be installed quite simply between the vacuum pump and the composite part. And what we do with this system is that it allows us to quickly identify if there are any leakages in the vacuum bag, which is essential to produce a high quality part in the end. So we have integrated different sensors into the equipment, pressure sensors for the vacuum level, but also flow sensors, volumetric flow sensors to identify gas flows. And based on the data from those two sensors, we are on the one side able to identify leakages, but also able to eliminate effects that come from the vacuum line. For example, when you have in production one vacuum pump for multiple parts and you disconnect or connect a new part, that gives some fluctuation in your vacuum level, and to eliminate that we have some algorithms in the system which allow us nonetheless to do precise measurements and precise indications if there are vacuum leaks. Also, we implemented some functionality inside this system to ease the manufacturing or the vacuum bagging of composite parts by implementing functions to control the vacuum level, for example, so that you can adjust the vacuum level at a pressure which is just slightly below ambient pressure, so that you can simply adjust your vacuum bag before you apply full vacuum. And this is easily provided to the operator, so we are reducing the human factor there. So going through the main features, one important feature that we included, because the sensors that we are using, they are limiting the flow, is that we also have a bypass. So when you have a huge part and a big vacuum bag, you want to evacuate that very fast, so you can also do that with our equipment. And after that, there are different steps which are also customizable, because the size of your part varies, the application or the scenario that you have in terms of the absolute vacuum that you can reach varies. So it's customizable, and also this vacuum control function that I mentioned is customizable. One important part also is that any dirt that comes from the part or from the setup is filtered out to eliminate bad measurements. And also one important point when it comes to using the system in a manufacturer or in a production environment is that we can also scan a work order and directly link the data that we are obtaining to the work order, so that it can be saved consistently and also saved in some database depending on the customer requirements. So for that, we also have different interfaces available to link it to any ERP system that you have, for example, so that you can store that data consistently and also trace it later on. What we are implementing right now is also a self-check function, so that we can directly check on the equipment if the sensors are operating correctly, to also ensure that there are no bad measurements. A quick look at the technical specification. As I already mentioned, we're working in the vacuum range, and we can really detect small leakages down to 12 milliliters per minute. If you come to our stand, we can show you how small that is, but it's really, really tiny. And we can control the vacuum level up to really a pressure that's just slightly below ambient pressure, so that you have the full ability to move your vacuum bag across. As I said before, there are different ways to communicate with our system, so we're quite flexible also there to adapt to customer needs, also when it comes to the interfaces in terms of the vacuum connections. And then, once we did the vacuum bag, the next part, at least for infusion parts, is to infuse the part with a liquid resin. And for that, we have a technology which we call inline infusion monitoring. And how this works is that we are using line sensors to identify where within the part we have resin and where we don't have resin. So this line sensor is basically a quite simple sensor consisting of two conductive strands, and our equipment creates a voltage pulse which we send through a coaxial cable into this line sensor. And at the beginning, when you have your dry part, what we obtain with our equipment is an impedance profile of the sensor. And when we have a dry part, this is an even profile, a dry profile, so we call that the dry level. We evaluate the data later on to give out an easy to understand interpretation of the flow front position. So that for that we split the sensor into 100 segments in most cases, and for each segment we give out whether we detected resin or not. So now we start the infusion, and in this case our sensor is impregnated at the beginning and at the end. So for example, we have race tracking along the edges. What our sensors can do now is that they can identify where this impregnation takes place. So we're not only saying 20% of the sensor is impregnated, but we can say the first 10% and the last 10% are impregnated. And we can then output that very easily to an operator by having a visual interpretation. Next step, there's also an additional flow inside the middle of the part, and also that we can pick up. So that's really the benefit, that we have a quite simple sensor geometry, but we get a lot of information out of it in terms of where we have resin in the part and in which direction the resin is flowing, which sets us apart from point measurements, which only provide point-wise information. And of course, then also in the end, we have the information that the part is fully impregnated, so the whole sensor reaches a homogeneous wet level, and we can then again output that to the operator. For different applications, we have different devices, a portable device which is mainly aiming at R&D applications, and also an industrial stationary device with also some slightly different connectors to be easier to use in industrial environments. And now we come to the sensors. There we also have different solutions, because we can say that different materials, in our case, require an adaptation of the sensors. So for R&D and prototyping, and also for carbon fiber materials and metal molds, we have line sensors which consist of wires, and they can be very easily positioned. And for integrating them, for example, also into RTM molds, we have special connectors, and then always, of course, the cables to connect them. We test, of course, the connectors for RTM, for vacuum tightness, and also for pressure tightness. And also we have connectors that, of course, prevent resin from flowing into the connector. So the sensor itself, in that case, is single use. It has to be positioned every time, but the connector, of course, is reusable. The other application that we are targeting, which is more relevant for industrial applications, is embedding sensors into molds. So there we are talking with our sensors about glass fiber applications. So there we can embed the sensor into glass fiber layers in the mold. So in this case, we have a carbon fiber layer also in there, but we need to embed the sensor below one layer of glass at the top of the mold, which protects it very well from scratches and so on. And in this case, we can also look through this layer of glass and into the part. And of course, this scenario of having the sensor integrated in the mold eliminates any redundant work of repositioning the sensor, and we're absolutely vacuum tight, and the mold can be used for multiple infusions. And then, when the part is cured, I will hand over to Benjamin again to explain you what we can do with the cured part.
Thank you. Yeah, so after curing, you can still continue to monitor your process, and the PF Inspect system that I told you about earlier on is also applicable for this application. With such a system, you are able to detect surface porosities. You won't have access to in-depth measurement. For this, you will have to turn to NDT solution, which are more classical solution that Testia can offer. However, you have access to information on the porosities on the surface, with criticality assessment of those porosities, telling you the depth of such porosities. You have also access to a final measurement of your fiber orientation. So for really aesthetic parts, it can be pretty useful to have this information, as well as information for little scratches on the surfaces. Finally, you get the 3D module that is available with the system, and that can allow you to perform final geometrical measurement on the final cured part. So today we were able to show you that our monitoring solution that Testia can offer can help you throughout your process, from the raw material up to the layup during vacuum bagging and infusion, up towards your final part. And you can find more information about all those technology, either coming to see us and the live demo that we've got on our booth. So we are located in all 6 in booth C43. Otherwise, you can always email us and feel free to consult our website. Thanks all for your attention, and if you have any question, we are happy to answer them. We have a question over there.
Thanks for the presentation, really nice work. I wanted to ask about the monitoring of the RTM during the infusion. So you show that you can have one line where you can predict where the resin is. So what if you have a more complex geometry? Will you have like multiple sensors to?
Yes, exactly. That's the idea. So our system can evaluate up to 16 sensors. So we have a multiplexing unit in there that can interrogate interrogates up to 16 sensors. And since we're multiplexing through them, they're really not interfering with each other. So it's also the possibility that you create a mesh, so that you place 8 sensors in one direction, 8 sensors in the other direction. Or you can also, if you have a very thick laminate, you want to get a information in Z direction about the impregnation, it's also possible to place multiple sensors in different, below different layers. So that's the option there. Because with the sensor itself, you said correctly, we are limited to inspecting really the area very close to the sensor. If you want to get more information across the whole part, you need to place multiple sensors. Yes.
Thank you.
Hello. Hello, I want to ask about the sensors, remaining existence of the sensors in the finished part. Does it create a weak point because it's not, it creates an ununiformed structure?
Yes.
It includes some other materials, a part of resin. Does it create some weak points after, during the performance?
We did some tests. So the sensors themselves, they are 0.2 millimeters in diameter, so they are very thin. The tests that we did, where we focused mainly on aerospace applications, so we did it with aerospace prepregs, and there we embedded the sensors in tensile testing samples and also compression testing. We did not do fatigue or anything in that direction. So with those first tests that we did not see an influence. So I would say if that's actually an application where it's essential that the mechanical properties of the part are met and we want to integrate the sensors, I would suggest to do specific tests with the sensors to make sure that there is no effect. What we saw so far is with the diameter of the sensors, with the tests that we did, with the material that we did not see an influence. Of course, I cannot generalize that, so we saw also that there's the compatibility with the resin was good, so there's no crack initiation or anything like that. Again, it's something that I would say, to be on the safe side, needs to be tested with the specific materials to make sure that there's no effect.
How about the long-term performance? Does it affect in the long-term?
That's not our focus, I have to say, in this case. So we are really focusing on monitoring the infusion process. So we are, with that application, really targeting process development, research institute or R&D departments investigating new processes, or where you have problems because you identify that you have porosity in your RTM part and you're suspecting that there's race tracking along the edges. For those applications, we're targeting with those sensors. So there, the long-term performance is not our main concern, because we're not actually aiming to put the sensors into flying parts or really parts that are produced for later use, let's say.
Thank you.
Any other questions? doesn't look like it. So I will, I think, conclude our speech. Thanks a lot for your attention and hope to see you soon at our booth.